Hello everyone, Assalamu alaikum. Welcome to Exam Essentials. Today we are going to solve the most common, important and difficult nature of light questions from the last 5 years. These questions are going to be very important for you guys. If you can master all of them, then you can solve any nature of light questions that will be thrown towards you by the examiners. So without wasting any more time, let's dive right in. This is a diffraction grating question from January 2020. It says, in an experiment, laser light is shown through a diffraction grating so that a series of bright dots appear on a screen. The equation n lambda is equals to d sin theta can be used to determine the wavelength of the laser light. Which of the following is a correct description of how the experiment should be performed? The first part says the angle theta is measured using a protractor. No, you can never ever measure the angle using a protractor. You guys can see right here. This is basically the angle between the central maximum and the first maximum. And right here we actually calculate this theta. How do you actually calculate this theta? In the question, this d is usually given. If they don't give the d, then you can actually figure it out. So in most common questions, the d is given, and this is basically the s which they also give us. If they don't give this d, we can actually calculate them, and this is the distance between the central maximum and the first maximum, which is generally given in the exam questions. If we have both of this, then we can definitely use tan theta to calculate this theta value. We never ever use a protractor. Okay. In the next part, it says the diffraction grating is set up so that it is parallel to the laser light beam. So they are saying diffraction grating is parallel to the laser light beam. Let's have a look at right here. We can see the beam is going in this direction, okay, which is vertical, and the diffraction grating is like this. So they are not parallel, actually they are perpendicular to each other. Okay, they are basically perpendicular to each other, so this cannot be our answer as well. Now the third question says the diffraction grating is set up so that it is parallel to the screen. Yeah, it's correct. As you guys can see, the diffraction, the screen on which the lights are going to produce the interference pattern is basically horizontal as well as the diffraction grating. So both of them are basically parallel to each other. So our correct answer is definitely going to be C. Okay. And let's read the part 3, option 3, to know why it is not the correct answer. It says the distance between the bright dots is measured with a micrometer. No, you never ever measure this distance using a micrometer. You use a meter rule or any other different ways. As micrometer is so small, it cannot measure this big line. Okay, you don't use such instrument to measure such big line. Okay, so that's it. Now let's move on to the next question. In 1924, de Broglie suggested that electrons have wave properties. The de Broglie equation states lambda is equals to h by p. Which of the following is correct? The de Broglie wavelength is independent of the mass of the particle. No, this is not basically correct. We know that lambda is equals to h by mv. So basically the mass is right here important. Okay, this formula can be used for the electrons or any other particles. Okay, this formula can be used for particles, and this formula can only be used for photons. Okay, when we write the same formula for photons, we cannot break it down like this when we write the same formula for photons, because the photons do not have any mass. So if you need to break down P, you cannot write mv for photons. You can only write mv for particles, no matter whether it is electron, neutron or proton. Okay, the same formula can be used for both of them, but this P cannot be broken down into mv for the photons. For photons, you will have to keep the formula like this. The second part says the de Broglie equation can be used to calculate the momentum of photon. Yes, exactly. We can use this formula to calculate the momentum of a photon, and we cannot break it down like this for photons because the photons doesn't have any mass. Okay. The term P represents the mass of an electron multiplied by the speed of light. No, the mass of an electron multiplied by the speed of the electron, not the speed of light. Okay. The value h depends on the particle involved. No, the h is a Planck's constant, which is always constant. Okay. And for photons, we do have another formula as well, which is E is equals to hf. This is another formula for photons, and we know C is equals to f lambda, right? C is equals to f lambda. So E is equals to hc by lambda. This is another formula that you guys should be familiar with. Okay, now let's move on to the next question. Alright guys, so now let's solve this very important question. It says the diagram shows refraction of a ray of light as it passes through three transparent substances L, M and N. The speed of light in the three substances are VL, VM and VN respectively. Which of the following should be the relationship between VL, VM and VN? Okay, they're talking about the velocity. They are just talking about the velocity right here. Now we'll have to actually draw normal in all the three parts. Okay, we'll actually have to draw the normals. So that is basically how we draw the normals. Now the question is, guys, we know one thing, that we can see right here the angle of incidence. This has to go like this, right? This should have gone like this, but this line has moved towards the normal. It has moved towards the normal, and we know the light bends towards the normal when it moves from less dense medium to high dense medium, right? So we can just write here that we can just write it down that it is less dense medium, and here it is more dense medium. And as the light has moved from less dense medium to more dense medium, that's why the light did bend towards the normal. And now in the next position, we can see right here that the light has moved away from the normal. From here it should have gone like this, but it did move like this, so it has gone away from the normal. So we can say it has moved from more dense medium to a less dense medium. The light has moved from a more dense medium to a less dense medium. All right, so we know the speed of light is inversely proportional to the density. Okay, the speed is definitely inversely proportional to the density. As the density increases, speed decreases. Okay, as the density increases, the speed decreases. So here the density is less, here the density is less, that's why the speed is more. But here the density is more, that's why the speed will be very less in this position. And here the density is less, that's why the speed is more right here. So we have been asked to compare between the velocities of the light in these three different parts. So where is the speed more? The speed is more right here, as well as the speed is greater right here. But in between this L and N, where the speed is going to be more? We can see towards the normal. You guys can see this L did make a larger angle with the normal. I mean, it is very much away from the normal, as it is very much away from the normal compared to this one. Yeah, here the speed of the light is good enough, or the speed of the light is large right here, but compared to N, at L the speed of light is more because it is moving away from the normal more compared to this one. So we can say the speed at L is greater than the speed at N, and here the speed is the lowest. So this is going to be Vm. VL is greater than Vn is greater than Vm. So our correct answer is definitely going to be B. Now the next part of the question, it says which of the following could result in a ray of light undergoing total internal reflection. Now in terms of total internal reflection, you will have to recall what are the criteria to fulfill total internal reflection. The first criteria is the light must move from more dense medium to less dense medium. Okay, the light must be moving from more dense medium to less dense medium. And the second thing is the angle of incidence should be greater than the critical angle, right? The angle of incidence should be greater than the critical angle. Okay, now right here they've given us the part C. Look at it, what it says. It says light traveling from M to L. So here, when the light is moving from M to L, at that time it is moving from more dense medium to less dense medium. So that's why C is going to be our correct answer. And as they didn't say anything about the critical angle, so we are not going to think about anything regarding the critical angle, because they didn't give us the angle of critical. They didn't give the critical angle, or neither they have given us the angle of incidence. Okay. And why this cannot be our answer? They're saying from L to M. So L to M means it is moving from less dense medium to more dense medium, which doesn't satisfy the criteria for total internal reflection. The next part says from L to N. L to N is also from less dense medium, covering from more dense medium to less dense medium. So it is also not covering the criteria of total internal reflection, which says from more dense medium to less dense medium. The next part says N to M. So N to M means again from less dense medium to more dense medium. So it is not satisfying the first criteria, which is the the light should be traveling from more dense medium to less dense medium, which only satisfies option C. So C is going to be our correct answer. Now let's solve this very tricky question. It says Earth and Jupiter orbits the Sun as shown. The distance from the Sun to the Earth is 1.49 into 10 to the power 11. So basically this is the distance from the Sun to the Earth, which is 1.49 into 10 to the power 11 meter. The distance from Jupiter to the Sun is 7.78 into 10 to the power 11 meters. So this is the distance between the Jupiter and the Sun. Alright. The next part says the intensity of sunlight at Jupiter is Ij. Which of the following can be used to calculate the intensity of sunlight at the Earth? Now we can actually use some formulas to complete this math. Okay. What do we actually know? We basically know that intensity is equals to power divided by 4 pi d squared, and this is the power output, and the power output of the luminosity the power output of the sun is basically constant. The power output of the sun is basically constant. It is the same, right? But the intensity on the earth and the Jupiter is different because of their distance from the sun. Okay, now what we can do is we can write this down for intensity of the Jupiter. Okay, we can write it down for the intensity of Jupiter. We can write intensity of the Jupiter is equals to power divided by 4 pi into distance of the Jupiter squared. Okay, we can write it down like this. And we can also write the same for the intensity of we can also write the same for the intensity of Earth. Okay, so we can write intensity of the Earth is equals to power divided by 4 pi into distance of the Earth from the Sun squared. So we can write both of them. Right, now we know power is the same for both of them, right? The power is going to be the same for both of them, so we can just make power the subject. Okay, both of these power are the same, right? They are constant, so we can write power is equals to intensity of J into 4 pi into d J squared is equals to intensity of the Earth multiplied by 4 pi into distance of the Earth squared, right? Now from here we can actually cancel out this 4 pi as well as this 4 pi. Both of them are cancelled out. Now what we are left with? We are left with only this, and they have asked us to make intensity of the Earth the subject of the equation. So we can write intensity of the Earth is equals to intensity of the J into dj squared divided by the distance of the earth squared. Okay, so my intensity of the earth is equals to this. So what is the intensity of the Jupiter? They didn't give us the intensity of the Jupiter, so we will have to write it in the formula. So we can also write intensity of the earth is equals to intensity of the Jupiter into distance of the Jupiter was 7.7 into 10 to the power 11. So 7.78 into 10 to the power 11 squared divided by 1.49 into 10 to the power 11 squared. So our correct answer is definitely going to be A. Hopefully you guys have understood it completely. Now this question says the diagram shows an electron transition between two energy levels in a hydrogen atom. Which of the following could not have caused this transition? The atom absorbing a photon with energy of 13.6 electron volt. I mean, we know that the electron is going to go up, right? When the electron has to go up, at that time he absorbs a photon, but he only absorbs the photon with an energy. Let's have a look at this. Since energy levels are discrete, an electron will only absorb and emit photons with energies equal to the difference between the energy levels. It will only emit and absorb energy with an energy difference between the energy levels. So as he is going to go up from minus 13.6 to minus 3.4, what is the difference between the energy levels? The difference between the energy levels is 10.2 electron volt. He is going to receive 10.2 electron volt of energy to move from this lower energy level to higher energy level. It will not receive 13.6. It will only receive the amount that is required to move from the lower energy level to higher energy level. It will never ever release 10.1 or 10.4 even. It will only receive this value, which is 10.2 electron volt. Please read it again. Energy levels are discrete. An electron will only absorb and emit photons with energies equal to the difference between the energy levels. It will never ever receive anything more. So this is not our correct answer, and this is going to be the answer actually, because they have said which of the following could not have caused this transition. This is the way why the transition could not actually happen. Okay, this is the way the transition cannot happen, because it will never ever absorb 13.6 electron volt. It will always absorb the energy value, which is the difference between the two energy levels. Now the next part says the atom absorbing a photon with an energy of 10.2 electron volt. Yes, this is correct, because as it will be moving from 13.6, sorry, minus 13.6 to minus 3.4, it will always absorb the energy, which is the energy difference between the energy levels, which is 10.2. Now the next part it says an electron with a kinetic energy of 13.6 electron volt colliding with the atom. Okay, so yeah, it can actually happen. Okay, it can actually happen. So when an electron with a kinetic energy of 13.6 electron volt collides with the atom. Okay, I have written the explanation right here actually. Okay, let's say this electron which is going to collide with the atom. Now this electron actually requires 10 electron volt. I mean, this electron requires 10.2 electron volt to move from lower energy level to higher energy level. But this electron has 13.6 electron volt, and this electron is going to collide with the atom. So when this electron collides with the atom, the electron from the atom, this electron inside the atom will only take 10.2 electron volt from this electron, and it will move from lower energy level to higher energy level. Okay, and the rest of the 3.4 electron volt will be left with this electron. This will be the kinetic energy of this particular colliding electron. Okay, now in the next scenario, let's say this electron requires 10.2 electron volt to move to higher energy level. Now this electron has exactly 10.2 electron volt. So now this electron inside the atom will take exactly 10.2 electron volt from the colliding electron, when the colliding electron will collide with the atom to move from the lower energy level to higher energy level. Okay, this is basically the explanation that I have written. When an electron with 13.6 electron volt collides with an atom, it transfers energy to the atom's electron. If the atom's electron needs 10.2 electron volt to move to a higher energy level, that amount energy is used, and the remaining 3.4 volt stays with the colliding electron as its kinetic energy. In another case, if the electron colliding with the atom has exactly 10.2 electron volt, all of that energy could be absorbed by the atom's electron to jump to a higher energy level. Therefore, in both scenarios, the atom's electron absorbs energy to move to a higher energy state, and any excess energy from the colliding electron remains with it. So this is a very important concept that you guys must master. So all of them are actually correct except this one. That one was the wrong answer, and they have asked which could not have caused this transition. So this type of knot is very important to see at the exam paper. Otherwise you could have actually corrected any one of them. The question was asking which was wrong. Okay, now let's move on to the next question. Now let's solve this question. It says the diagram shows some of the energy levels for a hydrogen atom. Which of the following expression is equal to the lowest frequency of light possible from a transition between these energy levels? So right here, the lowest frequency is basically required. Okay, the lowest frequency is basically required. So we know there is a formula which is E is equals to HF, right? E is equals to HF, and right here we need the lowest frequency. So as we need the lowest frequency, so for the lowest frequency there should be lowest energy change, right? There should be lowest energy transition. There should be lowest energy transition. So right here, if we make F the subject, it becomes E divided by H is equals to basically the frequency, right? And H is basically the Planck's constant. Now right here, if a hydrogen atom moves from this energy level to this energy level, what will be the difference in the energy levels? This is the final and this is the initial. So what we can do is we can do minus 2.42 minus 5.42. So this will give us a value of 3. There's a change in energy levels of 3 if it moves from this to this. It's going to be 3 joule. Okay, 3 into 10 to the power minus 19 joule. Okay, it is going to give 3 into 10 to the power minus 19 joule. Alright guys, so now let's solve this question. It says the diagram shows some of the energy levels for a hydrogen atom. Which of the following expression is equal to the lowest frequency of light possible from a transition between these energy levels? So basically we are looking forward to have the lowest frequency. Okay, we know there's a formula E is equals to, del E is equals to HF, right? Here we are going to make frequency the subject, so it becomes del E divided by H. Now this del E means the energy transition or the change in energy. Okay, now when a particle moves from 0 to 1.36, here the energy we are talking about is basically the photon that will be released, and we know a photon is only released when an electron moves from higher energy level to lower energy level. That's why we're going to go down. In this question you cannot think it of moving up, because when it moves up, at that time the electron or the atom or the electron from the hydrogen atom basically absorbs the photon. Now right here, as it is going to emit the photon, that's why it's going to come down. Okay, so if it comes from 0 to 1.36, the energy transition will be 1.36. okay, it is going to be 1.36, which is a bigger value. Okay, now when it comes from 1.36 to 1.42, at that time the energy transition is going to be exactly 1.06, a little bit smaller than the previous one, right? In the next part, when it comes from this path to this path, at that time the energy transition is 3, so it is even bigger. So right here, as we need the lowest frequency, so the energy transition should be the smallest one. So right here the perfect match will be this one, right? This one will be my perfect match. So I'm going to give the energy transition from 2.42 minus 1.36 into 10 to the power minus 19. Okay, I'm going to give this divided by the h, which is my Planck's constant, 6.63 into 10 to the power minus 34. So my correct answer is definitely going to be D. Okay. Alright guys, so now let's solve this question number 14 from the year January 2021. It says, the diagram shows some of the energy levels for an atom of hydrogen. When an electron with a kinetic energy of 12.3 electron volt interacts with this atom, an electron in the atom moves from minus 13.6 electron volt to minus 1.5 electron volt level. Okay, so basically it will be moving from minus 13.6 to minus 1.4 electron volt. Okay, so what is the energy change? The energy change is basically minus 1.5 minus 13.6, which is going to give us a value of 12.1 electron volt. All right, so if 12.1 electron volt is used, basically the kinetic energy of the incoming electron was 12.3 electron volt, and out of this 12.3 electron volt, 12.1 will be used by the electron to move to a higher energy level. So 0.2 electron volt will be remaining as the kinetic energy of the incoming electron. This will remain as the kinetic energy of the incoming electron. Okay, this is going to remain as the kinetic energy of the incoming electron. This is something that I've made you guys understand before while doing the multiple choice questions. In the next part it says, when a photon with a photon energy of 12.3 electron volt is incident on this atom, the electron in the atom at minus 13.6 electron volt remains at the minus 13.6 electron volt. Yes, this is because there is a criteria of photon. That is, what was the energy required for the electron to move from the lowest energy level to a higher energy level? It was minus 12.1 electron volt. And for photon, the photon had an energy of 12.3 electron volt. Now, in terms of photons, what happens is the photon energy is 12.3, whereas energy that was required to move from lower energy level so to higher energy level is basically 12.1 electron volt. So these two values are not the same, and photon has a tendency that it only gives their energy, it will give all of its energy, or it won't give at all. So right here only 12.1 is required and it has 12.3, so it cannot give all of its energy, so it will not give the energy to the electron, and the electron will not move from the lower energy level to the higher energy level. The photon has a tendency to give all of its energy. If he cannot give all of its energy, then he is not going to give the energy at all. So as he cannot give all of its energy to the electron, as the electrons energy levels are discrete, it only takes the amount of energy it requires, and it also gives all the energy that he has, as he cannot give all of his energy and he cannot take all, as he and the electron doesn't need all the energy to move from lower energy level to higher energy level. That's why with the photon no energy transition actually occurs, and our answer is going to be like this. Okay, our final answer is going to be like this, which says that the electron in the atom move from minus 13.6 to 1.5 requires 12.1 electron volt. 0.2 electron volt is the remaining kinetic energy of the incoming electron. But photon can only accept an electron if it matches the energy difference between levels. Photons gives all of their energy or none at all. Okay, photon's energy is not exactly 12.1 electron volt, so the electron remains at minus 13.6 electron volt, as the photons gives all of their energy or none at all. So that is going to be your answer for this question. Hopefully you guys have understood it completely. Now let's move on to another. Alright guys, so now let's solve this. It says light of wavelength lambda traveling at speed c is incident on a metal surface. Photoelectrons are emitted from the surface with a maximum kinetic energy. The graph shows the relationship between 1 by lambda and half mv square. Which of the following shows how the gradient of the graph can be calculated to determine the Planck's constant h? Okay, now here what we can understand is that light is incident on a metal surface and photoelectrons are emitted. Okay, photoelectrons are emitted. Now right here, no matter whether the photoelectrons are emitted or not, actually depends upon the energy of the light that is incident on the metal surface, right? If the energy of the light is greater than the work function that is required or that should be fulfilled for the photoelectrons to be emitted, then only at that position the photoelectrons will be emitted, right? So the formula is energy is equals to work function plus the kinetic energy maximum, right? Now this energy can be given as HF is equals to phi plus half mv square max, right? Okay, or we can also keep it down as kinetic energy max as well. Okay, we can also keep it down as kinetic energy max as well. So we can just write it down like this, kinetic energy max. Okay, now this HF can be written as HC by lambda. Why are we going to take it as lambda? Because the y-axis includes the lambda, is equals to phi plus kinetic energy maximum. And then we can just write 1 by lambda into Hc is equals to phi plus kinetic energy max. And this Hc can be divided on the other side. So we can just write 1 divided by lambda is equals to phi by Hc plus 1 by Hc into kinetic energy maximum. Okay, now right here we know our y-axis was 1 by lambda and our x-axis was half mv square mx. So here this is going to be my this is going to be my x-axis, this is going to be my x-axis, this is going to be my y-axis. Okay, this is going to be my y-axis, and if this is my x-axis, this is definitely going to be my gradient, and this is my y-intercept. Okay, now as my gradient is 1 by hc, okay, so if I make h the subject, 1 by hc is equals to gradient. So if I make h the subject, it becomes 1 by c into m is equals to h. Okay, so our correct answer is definitely going to be B. Alright guys, so now let's solve this 6 marks question, which is an asterisk question. It says the student used two sources of radiation to investigate the photoelectric effect for two different metals, copper and zinc. The following statement were made by the student. When radiation of photon energy 2 electron volt from source A is directed towards either of the metal, no electrons are released. As we can see that no electrons are released, what does that mean actually? It means that the photon energy of 2 electron volt was basically less than the work function of the metal plates, right? It is less than the work function of the metal plates. Okay, or we can also say that the frequency of source A is less than the threshold frequency of either of the metal plates. Okay, it is less than the threshold frequency of either of the metal plates. Okay, okay, now in the next part, what does it says? Even when the intensity of radiation is increased. What does the increase in the intensity means? If you increase the intensity, the number of photons incident is basically increases. Okay, now the next part it says when radiation of photon energy 4.4 electron volt from source B is directed towards the copper plate, no electrons are released. What does that mean? That means that the work function of copper plate is basically greater than 4.4 electron volt. That's why no electrons were released. However, when the radiation is directed towards the zinc plates, electrons are released. Okay, why the electrons are released? Because the work function of the zinc plate is less than 4.4 electron volt. Okay. In the next part it says as the intensity of radiation is increased, electrons are released at a greater rate. This is very common, right? What does intensity of radiation means? Intensity of radiation means the number of photons per second. If you increase the number of photons per second, we know each photon releases one electron. So if you increase the number of photons, then the number of electrons released will also increase per second. That's why the number of electrons released increases at a greater rate. Okay, that those are basically the points that you will have to understand and write. Now let's understand the mark scheme points, what the mark scheme says. And let's see whether we can understand or we have thought about everything that should be written. The first part says frequency of source A is less than the threshold frequency of the either metal. Correct? Because the source A couldn't actually release any electrons from either of the metal. So definitely the frequency of source A is less than the threshold frequency that is required to release an electron from the metal plates. Or you can also say frequency of source B is okay. Now let's compare with source B. Now in source B, it was able to release an electron from the zinc plate, but it wasn't able to release electron from the copper plate. So that's why we can say the frequency of source B was less than the threshold frequency of the copper plate, but greater than the threshold frequency of the zinc plate. That's why it was able to release electron from the zinc plate. That is basically what they have written. You can write either of them to get the first mark. Now the second part depends upon this part, that the photon energy from the source A, the photon energy from the source A was less than the work function for either of these metals. That's why source A wasn't able to release even one electron. And right here you can also say photon energy of source B is less than the threshold frequency, the work function of copper plate, but greater than the work function of zinc plate. That's why it was unable to release an electron from copper plate, but it was able to release electron from zinc plate. Okay. The work function for zinc must be between 2 volt and 4.4 volt. Why zinc will be between 2 volt and 4.4 volt? Because when 2 electron volt was applied, at that time no electrons were released from the zinc plate. But when 4.4 volt was applied, it released the electrons. So it must be greater than 2 volt and somewhere between 4.4 volt, the work function basically. Okay. And the work function of copper must be greater than 4.4 volt. As the work function of copper is greater than 4.4 electron volt, that's why the copper didn't release the electron upon the incident of this 4.4 electron volt photon energy. Now the next part says about the intensity of radiation had increased. What does the intensity of radiation means? The intensity of radiation means the number of photons incident per second. And as you increase the intensity of radiation, you are increasing the number of photons that are incident per second. And if more photons are incident per second, that means we know one photon can release one electron. So if more photons are incident on the incident per second, then more electrons will be released per second. So electrons are released at a greater rate. Okay, that is basically the points that you guys will have to understand very clearly, because those are assessed again and again in the exam papers. Make sure you understand each and every. Let's solve the question number 19 from the year October 2024. A photomultiplier is a device that can detect very low intensity light. In a photomultiplier, a metal plate called a photocathode is connected to the negative terminal of a power supply. Electromagnetic radiation incident on the photocathode can cause the photoelectric effect. The first question says describe the photoelectric effect. So what do we know about the photoelectric effect? We know that a photon will be incident on a surface and the photon will be absorbed by an electron. Okay, and that electron will gain energy and will be emitted from the surface, right? So that is going to be our answer, that a photon is incident on a surface and is absorbed by an electron. That electron gains energy from the photon and is emitted from the surface. In part B, it says the photomultiplier can only detect electromagnetic radiation that causes the photoelectric effect. Explain why the photomultiplier cannot detect some frequencies of electromagnetic radiation. We know the photomultiplier can only detect electromagnetic radiation that causes the photoelectric effect. So some frequencies of electromagnetic radiation are not detected. That means those frequencies are not able to create photoelectric effect. Which frequencies are not able to create the photoelectric effect, guys? We know to cause the photoelectric effect, the frequency of the photons must be greater than the threshold frequencies of the photocathode. If that is not satisfied, then the electrons will not be emitted and that will not cause the photoelectric effect, right? We know photons energy is proportional to frequency. So photons below a certain frequency cannot cause the photoelectric effect, and they won't be detected by the photomultiplier, something that I have been explaining throughout the session today. It says to cause the photoelectric effect, the energy of the photons must be greater than the work function of the photocathode. Photon energy is proportional to frequency. Photons below a certain energy or frequency cannot cause the photoelectric effect, and that's why they won't be detected by the photomultiplier. Okay, because those some frequencies have frequency less than the threshold frequency required to cause the photoelectric effect. Moving on to the next question, it says visible light has a range of wavelengths of this. The work function of the photocathode is 1.48 electron volt. Deduce whether the photomultiplier can detect all wavelengths of visible light. Okay, all wavelengths of visible light. Now we know a formula which is E is equals to Hc by lambda, right? We know E is equals to Hc by lambda. Now right here, we know the work function required for the material. Okay, the work function, we know the work function, this is the energy required. Okay, so this energy must be present right here. Okay, it must have that amount of energy, right? It must have that amount of energy. Now we can actually convert this energy into joule. Basically this electron volt can be converted into joule, so we can just write we will have to actually figure out the wavelength value. So to figure out the wavelength value, we can write it like this. We know the Planck's constant, which is 6.63 into 10 to the power minus 34, multiplied by the speed of light, which is 3 into 10 to the power 8, divided by the lambda. Okay, we can actually do the lambda right now. Oh, we are actually figuring out the lambda, so we can just divide by the energy. So we can just convert this into joules, which can be figured out as 1.48 into 1.6 into 10 to the power minus 19. Okay, so this will give us the value of wavelength to be 840 into 10 to the power minus 9 meter. So this wavelength is definitely greater than the wavelength value that must be right there. Okay, so 840 nanometer is greater than 700 nanometer. Now this will be detected. Why this will be detected? Because the wavelength value is the wavelength value up to which the photomultiplier can detect is basically greater than the wavelength region of the visible light, okay. So with this work function 840 nanometer of wavelengths can be seen. Okay, up to 840 nanometer of wavelengths can be seen, and visible light is less than that value. So yeah, definitely all of the wavelengths of the visible light can be detected. Okay, so we can just write all of the wavelengths of the visible light will be detected. I can actually explain this thing to you guys again. Why 840 being greater means that it will be detected. Okay. So right here, the visible region, the visible light has a region, the visible light has a range of wavelengths from this much. Okay, this is the range of the wavelengths from the visible light. Now it says the work function of the material used to make the photocathode is this. So we'll have to make sure that the energy is greater than this work function. Okay, the energy has to be greater than the work function. Okay, the energy has to be greater than the work function. Now deduce whether the multiplier can detect all wavelengths of visible light. Now we can just put this work function. Now if the if the energy of the photon is equal to the work function, it can still basically if the energy of the photon is greater than the work function, it can emit or it can make the electron to be released, right? So we have put this value right here. So for this energy we need a wavelength of 840 nanometer. 840 nanometer is required, and we have wavelengths less than that. Okay, we have wavelength less than that, which is, let's say, 700. Since the wavelength is less, so that photons will have greater energy than the work function, because for this work function the wavelength value is 840, but our actual wavelength value is even less. So as our wavelength value is even less, so our energy is even greater than the work function value. So yeah, it can detect all the wavelengths of the visible light. Okay, hopefully you guys have understood it completely. Now moving on to the next part of the question, it says in the photomultiplier, the photocathode and several other metal plates are in a vacuum as shown. An electron is emitted from the photocathode with a speed of this, right? An electron is emitted from here with this speed. There is a potential difference PD of 108 volt between the photocathode, this photocathode, and the first metal plate. So there will be a potential difference of 108 volt. This PD causes the kinetic energy of the electron to increase. So as it had some speed when it was released from the cathode, that means it does have some kinetic energy as well. And again, a potential difference is applied between the photocathode and the metal plate. So his kinetic energy will be even, his kinetic energy will increase even more because of the potential difference being applied. Calculate the kinetic energy in joules of the electron at the instant it collides with the first metal plate. So what will be his final kinetic energy at the first metal plate is what they have asked. So we can do one thing right here. We can actually figure out the kinetic energy of the electron when it is just emitted from the photocathode. We can just write half into the mass of the electron, which is 9.11 into 10 to the power minus 31. Wait, let me bring the thing right here. We can just do it like this. We can just figure the initial kinetic energy, which is half into the mass of the mass of the electron multiplied by this speed, which will give us the kinetic energy, which is the initial kinetic energy when it was just emitted from the photoelectrode, and then a further potential difference was applied to increase its kinetic energy even more. So we know this potential difference which was applied has done work on the electron. So we know work done is equals to charge into voltage, right? Here the voltage was 108 volt and the charge is 1.6 into 10 to the power minus 19. So this gives us, this is the work that the potential difference has done on the electron to increase its kinetic energy. So this was its initial kinetic energy, and this is the another work done. This work done is the increase in the kinetic energy of the electron. So the question says the kinetic energy at the instant it collides with the metal plate. I mean the final kinetic energy. So the final kinetic energy will be the initial kinetic energy plus the increase in kinetic energy, or the work done by the potential difference. So we add both of them and we get the final kinetic energy value. Hopefully you guys have understood it completely as well. Now in the next question it says the electrical circuit shown includes 4 resistors A, B, C and D, which apply a PD between adjacent metal plates. Each resistor has a resistance of 85 kilo ohm. So all of them have the same resistance. So as it's a parallel circuit, it is the series circuit, as all of them have the same resistance, they will get equal share of the voltage. In the next part it says when the switch is open, the PD across the supply is 1960 volt. So this is my EMF. Okay, this is my EMF. When the switch is closed, the PD across resistor A is 108 volt. So each and every resistor is getting 108 volt. So as all of them have the same resistance, so all of them will have the same voltage as well, equal share of the voltage. Okay, all of the resistors will get equal share of the voltage. Calculate the internal resistance of the power supply. Okay, for the internal resistance we know the formula is EMF is equals to voltage across the fixed resistors plus the voltage across the internal resistor. Okay, so it is saying voltage across the fixed resistors. So we know each of the fixed resistors has a PD of 108 volt. So how much will 4 of them have? It will have 4 into 108, and we know the EMF value was 1960 right here. the EMF value was 1960, plus the voltage of the internal resistor. We know the voltage of the internal resistor is equals to current into the internal resistance, right? Current into the internal resistance. Okay, current into the internal resistance. And now we'll have to actually figure out the current value. We have to figure out the current value. As it is a series circuit, the same current will be flowing through all the resistors, right? So let's talk about this resistor, which has a voltage of 108 volt and a resistance of 85 kilo ohm, right? So we can just do one thing. We know V is equals to current into resistance. So current will be equal to voltage by resistance. So we can just do right here like this, that here it will be voltage by resistance. The voltage value is 108 volt divided by 85 into 10 to the power 3. So we have write the current right here as well. And then you will have to just make this resistance the subject of the equation. If you make this resistance the subject of the equation, you will get the internal resistance value, which will be a value of 1.2 into 10 to the power 6. If you calculate by yourself, 1.2 into 10 to the power 6. So this is going to give us our final value. Hopefully you guys have understood it completely.
Let me guess. You are watching videos, taking notes, maybe even grinding late at night. But the marks, they are just not going up. You are stuck, and it's frustrating. But here is the truth, it's not your fault, it's the method. And that's exactly where Exam Essentials makes the difference. We at Exam Essentials actually offer two very powerful courses to navigate you towards success. The first one is the most popular high impact crash course. If you are just 4 to 6 months away from your exam, this course is going to be a lifesaver for you. And the second course that we at Exam Essentials actually offer is the complete 1 year course. This is basically for the students who want full support from day one to exam day. And the best part, our students' results speak for themselves. Both the courses are actually open ahead of every exam session. No matter whether you are going to give your exam for the May 26, Jan 27, May 25, or October 25, doesn't matter. We always offer these two courses before every upcoming exam session. To join or know more, just check the description box below. You will find our WhatsApp number and Facebook page link right there. Let's turn your effort into results together.
So now let's solve another question from the recent Physics Unit 2 papers. It says optical fibers can be used to transfer data. One optical fiber is made from glass with a refractive index of 1.5. The diagram shows a ray of light in air incident on the end of this optical fiber. Calculate the angle of refraction of the light as it enters the optical fiber. So they have basically asked us to figure the angle of refraction. Okay, now we know the light is traveling from air to the optical fiber, right? It is traveling from the air to the optical fiber. So we can write n1 sine theta 1 is equals to n2 sine theta 2. Now right here, you will actually have to understand one thing that has been given and again, that the angle should be with the normal. So it should be 40 degree. Okay. And we also know the refractive index of the optical fiber, which is 1.5. Now it will be very easy to actually answer this question. Okay, it will be very easy to answer this question. So this is how we will be answering this question. N1 sin theta 1 is equals to N2 sin theta 2. And this theta is going to be our angle of refraction. Okay, and we know the refractive index of air is 1. So that is going to be our answer. and here we have used sine 40. If you didn't recognize and start using sine 50, the answer is going to be wrong. Okay. Now the next part, it says the diagram shows one ray of light inside the optical fiber incident on a boundary with the air. Deduce whether the ray will be totally internally reflected at this boundary. Okay, so whether it will be totally internally reflected or not. Now right here as well, we'll also have to take the line with the normal, which is basically going to be 45 degree. Okay, this is going to be 45 degree. So this is going to be 45 degree. Now we'll have to figure out whether it is totally internally reflected or not. So for it to be totally internally reflected, the angle of incidence should be greater than the critical angle. We know the angle of incidence is 45 degree. We can just figure out the critical angle, and we know at the critical angle, the angle of refraction is perpendicular to the normal, right? Perpendicular to the normal. So we can just write sine c is equals to 1 divided by 1.5. Okay, we can just write it down. As we know, the refractive index of the glass is 1.5. So here C will be 41.8 degree. So we can see that the critical angle is less than the angle of incidence. As the angle of incidence is greater than the critical angle, so total internal reflection. You should not write like this. You should write total internal reflected in full words rather than in short words like me. Now the next part says data is transmitted along the optical fiber by pulses of light. One pulse of light initially has a constant intensity for a duration t as shown. Alright, light in the pulse can take different paths along the optical fiber. Okay, you guys can say one is moving straight, one is moving in zigzag lines, another one is getting out of the optical fiber. Shows three possible paths of rays of light in the pulse. Explain how the intensity and the duration of the pulse of light leaving the optical fiber are different from the pulse that entered the optical fiber. We know one pulse has multiple rays, right? All of these rays are from one pulse. So basically, one ray is moving straight, so his duration will be normal, but the another ray which is moving like this zigzag, it is covering more distance. As it is covering more distance, its duration will be less. First of all, we have to understand that different rays have different distance. Okay, and as they have different distance, they will have different time. They will take different time to travel from this end to the other end of the optical fiber. So as they take different time, the duration of this emerging pulse will be longer. Okay, the duration of this emerging pulse will be longer. And you can also say, we can also see that one ray is refracting out of the fiber. As one is refracting out of the fiber, now only out of the three rays, two rays are inside the optical fiber. So the intensity of the optical fiber will also decrease. Okay, and only one of them is moving straight, the other two is moving like this. So the overall duration of the pulse will also increase. Okay, now this is going to be our answer, that rays of light have different lengths and distances. We can see right here, one is zigzag, another one is straight, and the another one is like this. That's why. So different rays take different times to travel to the other end of the optical fiber. As they have different distance, so they will take different time to move to the other end of the optical fiber. And as all of them are not moving straight, all of the rays are moving in different ways. That's why the overall duration of the optical fiber, or the duration of the pulse basically, is going to be longer. Okay, because some of them are traveling like this, and all of these rays, the three rays basically includes one pulse. The pulses consist of three rays. So as three rays are taking three different time to move from one end to the other end of the optical fiber, so the whole pulse is going to take greater time, or the emerging pulse duration will be greater. And some rays are getting refracted out of the optical fiber, and as they are coming out of the optical fiber, we can say now less number of rays are present in the optical fiber, so the intensity of the pulse is lower because only two rays are present right now, as one of them did come out of the optical fiber. Now moving on to the next question, it says some optical fibers are surrounded by a thin layer of transparent material called cladding as shown. So this is basically my cladding and this was basically the glass. Okay, the transparent material has a lower refractive index than the glass of the optical fiber. Explain how the cladding affects the critical angle for the light at the boundary of the optical fiber. Now you will have to understand, before there was no cladding. Okay, before there was no cladding, there was glass and the air. Okay, there was, let's say this is the glass and this is the air. This was the glass and this was the air. So when there was only glass and air, at that time we know sin c is equals to 1 divided by n, right? But right now what do we have? We have glass and the cladding. So this cladding has refractive index greater than the air. Okay, the cladding has refractive index greater than the air. Now we can write the same formula, that sin c is equals to nc divided by the refractive index of the glass. So this nc is basically greater than the refractive index of air. So as nc is greater than n air, we know the refractive index is directly proportional to the critical angle. So now the critical angle is going to increase. Now the critical angle is going to increase. Okay, so this is basically the answer. We can just put it right here. Oh my god, you guys can just answer it like this, that the cladding has a refractive index greater than 1, or cladding has a refractive index greater than the air, so the critical angle is increased. Okay, so the critical angle is increased. That is basically the main thing. Okay, and that is how you guys should be answering this question. Now let's solve this very tricky question number 18 from the year May 2024. It says a camera includes a 5-sided glass prism. The diagram shows a ray of light incident on the prism at surface X. So this is basically the surface X. The ray of light is then transmitted to surface Y. Explain why the ray of light at surface X as shown. So what we can see at surface X, what we can basically see is the, the light has been transmitted like this. The light should have gone like this, but the light has bent towards the normal. So when the light bends towards the normal, we can understand that it has moved from a less dense medium to a more dense medium. And why did the light move towards the normal? The reason is because the speed of the light has decreased, and the refractive index of the glass is definitely greater than the refractive index of the air. That is the reason why the speed has decreased. So that should be our points which we should be writing. Okay, if you can write all of these points, then you are going to get 2 marks. You can either mention greater density or you can mention refractive index. Either of them will give you 2 marks, but make sure you write that the speed of the light decreases, or the light slows down when it enters the glass. Now the next part, it says at surface Y the ray of light must be reflected. So in this surface Y it must be reflected. Okay, this reflection could be due to total internal reflection. If the ray of light is not total internally reflected, the light can be made to reflect by applying a layer of silver to surface Y. Okay, deduce whether a layer of silver is needed on surface Y. Refractive index of glass used to make prism is given. So basically, indirectly what they have asked right here in this question is whether total internal reflection will occur or not. And we know for total internal reflection to occur, there are 2 criteria. The first criteria is the light must be moving from more dense medium to less dense medium. And when the light will be moving, at that time the angle of incidence should be greater than the critical angle. Now let's figure out the angle of incidence first. Now this is a very common type of thing that Edexcel does always. They always give the angle with something else rather than the normal. We'll have to draw a normal right here. We always have to figure out the angle of incidence or the angle of refraction with the normal. You cannot figure out from any other value. Okay, it has to be from the um, it has to be from the normal, and we know the normal is always perpendicular to the surface at which the angle is incident. Okay, now right here what we can see is this is 90 degree as a whole, right? As this angle, as the normal is perpendicular to the surface, so it is definitely going to be 90 degree. And if this is 53 degree, then this is definitely going to be 90 minus 53, right? This is going to be 90 minus 53. So that's how we are going to write that my angle of incidence is 90 minus 53, which is 37 degree. Now I have got my angle of incidence. Now to figure out whether it is totally internally reflected or not, we'll have to see about the critical angle. We'll have to figure out the critical angle, and we know the formula of critical angle is sine c is equals to 1 divided by n. Sine c is equals to 1 divided by n, and we know we'll have to make c the subject, and when we make c the subject it becomes sine inverse 1 divided by n, and n is the refractive index of the surface, or the refractive index from which the light is traveling. I mean the more dense medium from which the light is traveling. So here it is the refractive index of the glass, which is 1.52 as they have given us. So the critical angle is 41.1 degree, and as we can see that 41.1 degree is greater than 37 degrees, so our answer is going to be that it will be totally internally reflected. So a layer of silver is not required. And as the question said deduce, you will have to show mathematical and then write down why, what is the answer. Okay, so if you don't write the final answer, you're not going to get the last mark. So you'll have to write that 37 degree is greater than 41 degree. So total internal reflection, don't write like this, write completely. I'm just writing to save time. Will not take place. Why total internal reflection is not going to take place? Because the angle of incidence is less than the critical angle, whereas the angle of incidence should have been greater than the critical angle, and the surface must be layered with silver. Okay, and surface must be layered with silver, and that is going to give you your full marks. Okay, now moving on to the next question, it says the camera contains a light sensor. The camera can detect the number of photons incident each second on the sensor. The camera is going to actually detect the number of photons incident each second on the sensor. Okay, the sensor has a known surface area. Explain why knowing the number of photons arriving each second at the sensor cannot be used to determine the intensity of light incident on the sensor. Now basically if you know the number of photons, this is not basically enough. Why is it not enough? Because this cannot actually give us the intensity. What is the formula of intensity? We know intensity is equals to power by 4 pi d squared, right? Intensity is equals to power divided by 4 pi d squared. Now right here 4 pi d square is basically not in one, um, not actually linked with the number of photons. Now let's talk about the power. Okay, what does the power means? Power basically means energy divided by time taken. Power is basically means the energy of the photons that is incident per second on the sensor, right? The energy of the photons that is incident per second. And right here, what does intensity gives? Intensity gives the energy of the photon incident per second on per meter square area, which is E divided by T, which is divided by meter. So the thing is energy incident per second per meter squared. Okay, So none of them includes, the whole formula doesn't include the number of photons. So we cannot say anything, that we cannot say that the number of photons actually cannot be used to determine the intensity. So that is the main thing. Okay, because it is not included in the formula. Okay, so this is going to be our answer. Okay, we'll actually have to know the energy of the photon to figure out the intensity. We'll have to know the energy of the photon per second incident per meter squared to get the intensity. Okay, the number of photons are not going to help. The total energy of the photons is going to help us. So intensity is the energy per second per meter squared. Energy per second per meter squared, or intensity is equals to power by area. You can also write down this formula only to get the first mark, and the second mark will be rewarded if you can write the energy of each photon is not known. We know the number of photons, but we have to know the energy of each photon, which can be figured out is equals to hf. Okay, so that is why the number of photons arriving at each second at the sensor cannot be used to calculate the intensity of light. Okay, now moving on to the next part of the question. It says the light incident on the sensor causes a current in the circuit in the camera. Light with a power of 1 watt is incident on the sensor. Okay, so they have basically given us the power value. They have given us the power value that is incident on the sensor. The graph shows the relationship between the wavelength of the light and the current produced. The current is proportional to the number of photons detected per second. Monochromatic light with a wavelength of 600 nanometer is incident on the sensor. The power of the light is 1 watt. The question says determine the percentage of photons that are detected by the sensor. So right here they are talking about the percentage of photons that are detected by the sensor. Now we'll have to actually understand one thing. I'm going to bring that part right here. Okay. What is photons detected actually? What is basically the photons detected? They are saying right here that photons that are detected. Photons detected means photons that cause the emission of electrons. Okay. We know the photons that will be incident on the area, right? The photons that will be incident on the area. But not all of the photons will be responsible to emit the electrons. Not all of the photons will be responsible to emit the electrons. Only the photons that will be able to emit electrons are going to get detected by the sensor. This is a thing that we'll have to understand. Okay. So first of all, as they have said, the percentage of photons. We know, let's say 10 photons have come, but only 5 of them have been able to emit an electron. So what is the percentage of the photons that has been able to emit an electron is basically what they have asked. The percentage of photons that are detected by the sensor. Because the photons that are actually able to emit the electrons will be detected by the sensor. Okay. So now for this, we'll have to figure out the number of electrons that actually was incident on the sensor, or that was actually incident on the sensor. Okay, and then we can actually also figure out the number of electrons that were emitted. If we can figure out the number of electrons that were emitted, we can figure out, as we have, the incident means all the photons that have been incident on the sensor, but the electron will only show the number of photons which was actually detected by the sensor, because the sensor will only be able to detect those electrons which was emitted because of the photons. Okay, those photons has the um, energy greater than the work function to be able to release the electrons. Okay, now let's figure out the total number of photons that was incident on the sensor first. Okay, now let's figure it out first. Now to figure that out, we'll actually have to figure out the energy of one photon. We know the energy of one photon can be figured out by this formula, which is E is equals to hf, which can also be written as E is equals to hc by lambda, right? We can also use that formula. E is equals to hc by lambda can also be used right there. So using that formula, we know the wavelength value that they have given us, which is 600. So h is the Planck's constant, c is the speed of light, and lambda is the 600 nanometer that given us, which is to be converted into meter right here. Using that, we have actually figured out the energy of one photon. Now, as we have got the energy of one photon, now our next work is to do something else, which is we know that power is equals to energy divided by time taken, right? We know power is equals to energy divided by the time taken. And as power is equals to energy divided by the time taken, okay, now let's figure out the energy, okay, of photon that will be incident on the sensor per second. The energy of the photon, I mean energy of the photon that will be incident on the sensor per second. So here the time will be only 1. So here we can write P is equals to, this is the total energy, right? This is the total energy. The total energy includes the number of photons multiplied by the energy of one photon, right? And as the T is per second, so it is going to be 1 second. So we can just write the formula P is equals to number of photons into energy of one photon, right? We basically know the energy of one photon, and we also know the power value as well. We can just figure out the number of photons from here. So here the number of photons will be equal to the power that is incident on the screen, or sorry, incident on the sensor, and then the energy of one photon per second. Okay, per second, that's why it is 1 second. And if you divide anything by 1, it is exactly the same that it is. So the value will be this one, which is 3 into 10 to the power 18. This is basically the number of or the total number of photons that was incident on the sensor. Okay, this is basically the number of photons that was incident on the sensor per second. Okay, this is going to be per second. We are considering per second right here. Now they have also given us the current value that we can actually figure out. Okay, we know the wavelength was 600. So if this is 510, this is, sorry, there is a difference of 200 and there is 10 boxes right there. So this will be 520, this is 540, this is 560, this is 580, and this is going to be my 600. So I can take it like this, right? So this value, if this is 0 0.4, this is 0 0.42, 44, 46, 48, 0 0.5. So this is definitely going to be 0 0.41. 0 0.41 ampere is the current that will be basically that will be produced. Okay, so we have got the current value. Now we know there is a formula. The current that will be produced per second, we can actually figure out the current produced per second. The current produced per second, we know current is equals to charge divided by time taken. Since the formula is per second, so we can write current is equals to charge by 1. So current is equals to charge by 1 is the same as current is equals to charge. Now this is the total charge. What does total charge means? Total charge can also be written as number of electrons multiplied by the charge of an electron, which is 1.6 into 10 to the power minus 19. Okay, so what does the number of electrons mean? We can figure out the number of electrons. We know the current is 0.41, which is divided by 1.6 into 10 to the power minus 19 will give us the number of electrons right here. So we have got the number of electrons that was emitted from the sensor is basically this. So we have got the total number of electrons, sorry, the total number of photons that was incident as well as the number of electrons that was emitted. So we know not all of the photons have the energy greater than the work function to be able to emit an electron. So out of all of these electrons, only this were able to emit an electron, and this is the number of photons that will be detected by the sensor, because the sensor can only detect those. How will the sensor actually detect the photons? The sensor will only be able to detect the photons the sensor will be only able to detect the photons by looking at the number of electrons emitted, because one photon will only emit one electron. This is a very important part. So now the question says the percentage of photons that are detected by the sensor. So the percentage of photons detected by the sensor is the number of electrons emitted divided by total number of photons into 100%. So this is also basically the number of photons that had the work function greater work function had energy greater than the work function which was required to emit an electron, and only those photons were basically detected by the photons, and the other ones were not detected by the sensor. Into multiply by 100 will give us a value of 87%. So this is basically the percentage of photons that are detected by the sensor, okay, because they were able to emit electrons and they had energy greater than the work function. Hopefully you guys have understood this very tricky question from. All right guys, so now let's solve this question number 16 from the year October 2022. It basically says an optical fiber consists of a core material surrounded by a material of lower refractive index. So the core material is surrounded by a cladding which has a lower refractive index than the core. A ray of light approaches the boundary between the core and the cladding as shown. Show that the critical angle for light incident on the boundary between the core and cladding is 75 degree. Okay, so they are asking that whether the critical angle for the core and the cladding is basically 75 degree. They have asked us to show that, okay, that they are basically 75 degree. Now one thing that we'll have to understand is we know the light is moving from core to the cladding. So we know the formula is basically n1 sin theta 1 is equals to n2 sin theta 2, right? We have to take the refractive index, this one, and this sin theta 1 is basically the critical angle, okay, the critical angle. And we know the refractive index of the cladding, which is 1.43, and we know during the critical angle, at the critical angle, when the angle of incidence is equal to the critical angle, at that time the angle of refraction is parallel to the surface. So when it is parallel to the surface, or when we say it is parallel to the normal, when it is parallel to the normal, so it makes 90 degree with the normal, and as it makes 90 degree to the normal, that's why we have written sine 90, which is basically equal to 1. So here the critical angle value that we will be getting is basically 75.1, and this is basically the critical angle value that we have figured out. Okay, now in the next part it says explain what will happen to the ray of light after it meets the boundary between the core and cladding. That diagram is drawn to scale and you should use a measurement taken from the diagram. So you have to take measurement from the diagram. So you have to measure this angle of incidence from the diagram. Okay, and you cannot measure this angle basically. You'll have to draw a normal like this and then measure this angle. Okay, because we always measure the angles with the normal, and when you will measure this angle, you will get a value which will range from 79 to 81, and as this angle of incidence is basically greater than the critical angle that we have figured out, so we can say the light will be totally internally reflected, and we will have to write this is greater than the critical angle to get the 3 marks out of it. Okay, now the next question it says the path of another ray of light through the core of the optical fiber is shown. Calculate the time taken for the light to travel in a straight line along 70 km of its optical fiber. So it will travel 70 km in this direction in a straight line. Okay, in a straight line. So as it will be moving in a straight line, we'll have to actually figure out the velocity with which this light will be traveling. We'll have to figure out the velocity with which it will be traveling, right? Now we know it is in the core. As it is in the core, we know there is a formula of refractive index, that is n is equals to c by v, right? And here we can actually make v the subject, so it will become c by n. We know the refractive index of the core in which the light is traveling. Okay, so we can figure out the velocity from there, and we can use that velocity with this distance. We know velocity is equal to distance divided by time taken. We can just divide the velocity by that. We can just divide the distance by the velocity to get the time taken from it. Okay, that is what we can actually do. So that is going to be the way that we will be actually doing the math. Okay, this is basically the way we'll be doing the math. N is v is equals to c by n, from where we'll actually figure out the velocity of the light traveling in this core. Okay, traveling in this core. When it travels in the air, the speed is this, but when the speed of light in the core is basically this. Okay, and then time is also distance divided by speed, distance divided by speed. So distance divided by the speed, as it will be covering 70 kilometer, the time taken for it to travel the 70 kilometer can be figured out like this. Now the next part of the question, it says light may escape from the core into the cladding when the optical fiber is curved. The student suggests that using a cladding with a lower refractive index would lead to less light escaping from the core. So less light will be escaping from the core. Now the student is basically correct in my opinion. Okay, because when you use a lower refractive index, when you use a cladding with a lower refractive index, what actually happens? We can actually go back to this formula. Okay, we can actually go back to this formula. If you make this C the subject, it becomes C is equals to sine inverse 1.43 divided by 1.48, right? And what is this 1.43? This 1.43 is basically the refractive index of the cladding, right? Refractive index of the cladding. Okay, so as the refractive index of the cladding gets smaller, the critical angle gets smaller, right? As the refractive index of the cladding gets smaller, the critical angle gets smaller, and when the critical angle is smaller, at that time more light will be total internally reflected. Okay, and as you won't require very high angle of incidence. Okay, because more of the incident light will hit the boundary at an angle greater than the critical angle. That is the reason. Let's read the question again. It says light may escape from the core into the cladding when the optical fiber is curved. A student suggests that using cladding with a lower refractive index would lead to less light escape. Why less light will be escaping? Because more of them will be reflected back into the core and less will get the chance to refract. Okay, less light refracted, more light total internally reflected. Okay, and why more light total internally reflected? Because when you use a smaller refractive index, the critical angle gets smaller. So when the critical angle gets smaller, most of the angle of incidence, or the most of the incident light will hit the boundary at an angle greater than the critical angle. Okay, so these are going to be our explanations. So lower refractive index leads to lower critical angle. So more light total internally reflected, less light refracted. And another thing that you can write is more of the incident light will hit the boundary at an angle greater than the critical angle. You don't need the third line, but I'm actually writing it to make things a bit easier for you. More of the light, the incident light, which will lead to total internal reflection and less light escaping from the core, because less light will be refracted from the core into the cladding. Okay, hopefully you guys have understood it completely. We're going to solve another very important question, which is going to clear a different type of concepts which will help you on the exam day. Now it says, after an atom of hydrogen has been exposed to suitable electromagnetic radiation, the atom can emit visible light. Okay, now basically a hydrogen atom has been exposed to electromagnetic radiation. What does electromagnetic radiation means? We know electromagnetic radiation means photons. Photons are electromagnetic waves. Okay, so you are exposing a hydrogen atom to the electromagnetic waves. Okay, so this, you can think it of like this, that this is an atom is exposed to electromagnetic wave. Photon is an electromagnetic wave. So when the photon will be moving, at that time this electron will absorb a photon, okay, and then move to higher energy levels. Okay, it will move to higher energy levels. The next line says the emitted light contains a small number of different wavelengths of visible light. Okay, so we know that electron when moves to a high energy level, it is unstable, it cannot stay right there, it will again fall back, and when it falls back it emits. So when it falls back, it basically emits the photon that he has actually absorbed. Okay, he actually emits the photon that he has actually absorbed. So that photon, that particular photon will have a wavelength which will be on the visible region of the spectrum. Okay, that will be on the visible region of the spectrum. That is what said. The emitted light contains a small number of different wavelengths of visible light. So the photons that it will be emitting, a couple of a different type of photons will have different wavelengths, but all of them will be in the visible light. Okay, now just explain the process that results in the emission of a different wavelengths of visible light. Your answer should include reference to energy levels in the atoms. Now in the first line you guys should be writing, I can actually break the point right here, which you can actually going to use right here. This is going to be our answer. Now let's understand from here. The first line that we are going to say is the electron is going to absorb energy from the electromagnetic wave, and after absorbing the energy, it will be moving to higher energy levels. This will give you the first 2 marks, and we know it is unstable right there, so it will again fall back. Okay, and when it falls back, it releases the photons. This is going to give us the 3rd mark. The 4th mark that you guys must remember, that energy levels are discrete. What does energy levels are discrete means? That for hydrogen, let's say, to move from the ground state to the first excited state, it takes the energy level difference is basically 10.2 electron volt. Okay, it is 10.2 electron volt. But let's say for if it wasn't a hydrogen atom, for sodium atom, the difference would have been actually different. Okay, that is what says that the energy levels are basically discrete. And now the 5th point that you guys should be writing is, for hydrogen atoms, there are only a small number of possible energy level differences that can occur to produce visible light. As the question was saying, that emitted light contains a small number of wavelengths of visible light. So you cannot take all the photons. Okay, you cannot take all the photons. Let's say if the electron move from this energy level to this energy level, when it will fall back, it will release a photon, right? That photon will be from the visible light spectrum. The wavelength of that photon will be from the visible light spectrum. But if the electron moves from this position to, let's say, here, at that time the difference is, let's say, 13.06, and that difference in energy levels is very huge. So now the photons that will be released, will not be in the visible spectrum. So for the hydrogen atom, there is only very small number of possible energy level differences that can occur to produce the visible light. Okay, basically the first 2 ones, from the ground state to the excited state, and maybe the second state as well. But you will have to understand one thing, that very small number of energy levels are basically available for hydrogen, which will produce visible light. Okay, and we know energy is equals to hf, which can also be written as energy is equals to hc by lambda. Okay, so as only small number of energy levels differences are basically available for hydrogen to produce visible light, so as small number of energy levels are possible, so only certain wavelengths are also emitted. Only certain wavelengths are only emitted as well, because if more energy levels were possible for hydrogen atom to produce visible light, then more different wavelengths of photons would have been emitted. But as only a certain number of possible energy level differences can produce visible light, so only a certain wavelengths will be emitted from that energy level differences. So that is going to give you your 6 marks. Hopefully you guys can understand the whole concept very easily. Now let's solve this very tricky question number 14 from the year October 2021. It was an uncommon question, to be honest. It was never repeated again in the last 4 or 5 years. That's why I've taken this question. It says a gold leaf electroscope is used to demonstrate the photoelectric effect. When the zinc plate of the electroscope is given a negative charge, as this is connected with this conducting rod, as well as the zinc plate, the conducting rod is going to become negatively charged. And that is what happened. The conducting rod and the gold leaf also become negatively charged. And as this gold leaf is connected with the conducting rod, both of them are negatively charged, so are repelled. And as the negative charge is repelled, the gold leaf has become like this. It has deflected. Okay. Now it says the gold leaf deflects away from the metal stem as shown. The deflection of the gold leaf depends on the amount of charge on the zinc plate and the conducting rod. Okay, we all know that thing. The next part says a beam of ultraviolet radiation is incident on the zinc plate. The gold leaf immediately begins to fall back to the conducting rod. Explain why this observation cannot be explained by the wave model of electromagnetic radiation. Now this is a very important part. When um, the when the ultraviolet radiation was incident, okay, when the ultraviolet radiations was incident right here, when the UV radiation was incident, we know that the UV radiation will release photoelectrons or emit photoelectrons from the zinc plate, right? And it says that immediately as electrons are removed, now this is becoming less negatively charged, so the electron will come back. So the gold leaf will come back to the conducting rod. So it says the gold leaf begins to fall back to the conducting rod. Everything was fine till now, but the question says the wave model. Now you have learned about the photoelectric effect. What about the wave model? Now what is the difference between the wave model and the photoelectric effect? The biggest difference between wave model and photoelectric effect is, in wave model, what do we say in photoelectric effect? In photoelectric effect we say if the photons that will be coming has a certain frequency which is greater than the threshold frequency of the zinc plate, then electrons will be emitted immediately, right? Electrons will be emitted immediately. But in wave model, what do they say is the energies will be spreading on this zinc plate. Okay, then there will be a build up of energy in the zinc plate, and it takes time for that energy to build up in the zinc plate. And when that energy will build up in the zinc plate, at that time the electrons will be emitted. So it is not emitted immediately, it takes time for the energy to build up. Okay, so that is the difference between the wave model and the photoelectric effect. That's what I have written as a note right here. I have given this one for you guys to read. Energy builds up over time and electrons are not released immediately, cannot be explained by the wave model. They have said this one, right? This cannot be explained by the wave model because according to the wave model, energy from light spreads evenly across the surface and should accumulate gradually until electrons have enough energy to escape. So it will take time. Okay, and the energy spreads evenly across the surface. But in reality, electrons are emitted instantly when light of sufficient frequency hits the surface. Something that we've seen in photoelectric effect. No matter how weak the light is, it must has if it has the sufficient frequency, it can emit electrons. Okay, this immediate emission shows that energy is delivered in discrete packets, not a continuous wave, proving that particle photon model of light, not the wave model, explains the photoelectric effect. Okay, so that is the main thing. So as it is saying immediately cannot be the wave model. Immediately is basically the photoelectric effect, okay, or the particle nature of light, not the wave model. In the wave model, everything happens gradually because there must be a build up of energy. Okay, and then basically the electrons can escape. Without the build up of energy, it cannot escape immediately. So that's what our final answer should be like. Okay, in the wave model, energy is built up over time. Okay, in the, or you can also write, in the wave model the energy is spread across the wave. Either of them will give you the first mark, but for the second mark you should write in between these two, one between these two. So photoelectrons would not be released immediately or instantaneously. Photoelectrons would be released after a time delay. Okay, the same thing but written in two different ways. So you can take one from here and the one from here to answer it. And I have explained it in so detail right here as well. So make sure you are having a very close eye on this question. Alright guys, so now let's solve this question number 17 from the year October 2022. It says a red light emitting diode was placed into a circuit as shown. The light emitting diode emits light of wavelength 627 nanometer and may be assumed to be 100% efficient. Alright, very good. The battery has negligible internal resistance. The switch was closed. The reading on the ammeter was 9.2 milliampere. They have asked us to figure out, show that the power was 0.1 watt. We know the power, right? The power is equals to voltage into current. So power is equals to voltage into current. We know the power, the voltage value is 12 volt and the current value is 9.2 milliampere. Okay, so we can just do the math. It will be like this: 12 into 9.2 to 10 to the power minus 3, which will give us a value of 0.11 watt. And in the show that questions, you have to remember one thing, that the value that they will ask you to show is, let's say, in 1 SF, but in your final answer should be one significant figure greater than the value that they have asked you to show. They have asked you to show 0.1. You will have to write 1 SF more. If you don't write it, then you will be penalized 1 mark. That is strictly said by Edexcel. So make sure you maintain this rule. Okay. The next part of the question says calculate the number of photons emitted by the LED in 1 minute. Okay. They have asked us to figure out the number of photons emitted by the LED in 1 minute. Okay. So the number of photons. This is a very common question which I actually explain to my students again and again, and I did explain that previously as well. So the number of photons emitted by the LED in 1 minute. So we'll have to understand the total energy, okay, emitted by the LED. Total energy will be equal to the energy of one photon multiplied by the number of photons. Okay, so we know the power value, so we can actually figure out the energy that was basically the total energy that was emitted by the LED in 1 minute. We can figure out the total energy that was emitted by the LED in 1 minute. Okay, so we can just do this thing, that we know energy is equals to P by T. We know the power value. We can just put 60 seconds right here and can figure out the total energy that was emitted by the LED in 1 minute. So energy is equals to power into time. Sorry, my bad. I've written the formula in a different way. It should have been power is equals to energy divided by time taken. So energy is equals to power into time taken. So it gives a value of 6.6 joule. This is the total energy that the LED did emit in 1 minute. I have got the total energy. Now I will have to figure out the energy of one photon, and the best formula to figure out the energy of one photon is E is equals to HF, right? Or you can also use E is equals to HC by lambda. Okay, we know the Planck's constant value, which is this one, multiply by this 3 into 10 to the power 8 divided by 6.27 into 10 to the power minus 9 will give us a value of 3.17 into 10 to the power minus 19 joule. Or you can do it in the way of the examiner as well. You can first figure out the frequency, because you know the wavelength of 620 nanometer. You can just put it right here. Okay, you can just put it right here. You can figure out the frequency and then use E is equals to HF. Using this, you have got the energy of one photon. You have the total energy, you have the energy of one photon as well. Now it's just a matter of time to figure out the number of photons. You can just divide the total energy that you have figured out right here divided by the energy of one photon, and you will get the number of photons. It was a very easy peasy lemon squeezy question, but it is very important to be able to answer this question. Make sure you understand it well. Now in the next part of the question, it says the red LED was replaced with a green LED which emits with a shorter wavelength. So it emits shorter wavelengths. The current in the circuit did not change. Explain how replacing the LED affects the number of photons emitted in 1 minute. So what does shorter wavelengths means, guys? If something has a shorter wavelength, then the energy of the photons, energy of one photon will be greater, right? The photons that it will be as the red LED has shorter wavelength. I mean, the red LED is emitting light with shorter wavelengths. So what does that mean? That lights will have, or let's say the photons from that light has shorter wavelengths. That means the photons from that light have greater energy. So each photon have greater energy. Now if each photon has greater energy, now the total energy is constant, right? The total energy is constant. If the total energy is constant and each photon is now exerting more, each photon has now more energy. Let's say I know one thing, that energy of one photon is equals to total energy divided by the number of photons. So if energy of one photon increases, the total energy remains the same, so the number of photons will definitely decrease, right? So that is going to be our answer. Okay, and why did I say that the total energy of the photons remains the same? Why? Because the current in the circuit doesn't change, and if the current in the circuit doesn't change and the EMF is also constant, that means the power value is also constant, and if the power value is constant, then the total energy incident from the LED, or the total energy from the LED, is going to remain also constant. Okay, so that is going to be our answer, that lower wavelength leads to greater photon energy, therefore fewer photons in 1 minute. Hopefully you guys have understood it completely. Now moving on to the next question, it says the maximum intensity of sunlight at the earth's surface is this. All right, a student suggests that the intensity of the light at a distance of 5 mm from an LED with a power of this is greater than the intensity of sunlight at the earth's surface. So to figure out whether this intensity is greater than this intensity, we'll have to figure out this intensity. We know the intensity formula is intensity is equals to power divided by 4 pi d square. So we have got our power. We'll just do 4 pi into 5 into 10 to the power minus 3 squared, because it is in millimeter. We'll have to convert it into meter. So now let's bring the answer and look at like this. So area is going to be 4 pi into d square, where the millimeter has been converted into meter. We have got the area, and intensity is equals to 0.69 divided by this area. We'll get the intensity as 2196. As this intensity is greater than the intensity of light at the earth's surface, so we can say the student's statement is correct. So we can just write it down like this. So the student is, make sure to write this final statement, otherwise you will not get the third final mark despite doing the math correctly. So the student is correct, as the intensity of light from LED is greater, you should write greater in words actually, is greater than the intensity at the earth's surface. So that is going to be your final words, which will give you the last mark. Otherwise you are going to lose 1 mark despite understanding the question and writing it correct.